Hello and welcome back. Today we're going to start on the second to last module here. It is the Wednesday, first Wednesday of the month, so of course we're going to have our uh, tornado drill here. Hopefully it won't last that long, but hopefully you only hear it in the background. So sorry about that. Today we're going to start talking about dynamic programming. And at its core, well, first of all, dynamic is not really, there's really nothing dynamic about it. Dynamic, in fact, literally, it was just a fancy marketing term. This might be apocryphal, but the what I've read, the person that came up with this basically was trying to sell his research to the Department of Defense or some government agency or like something like that, and so he came up with a term dynamic programming, so that he could sell that and get funding for his research. At its core, the basic idea is basically what we've looked at before. It's a divide and conquer approach to problem solving. Right? And you might have seen this before in at least glimpses of dynamic programming. But basically, whenever I try to introduce recursion, I try to show why it's bad, or at least some of the pitfalls of recursion. In that you are repeatedly doing the same computations over and over and over again. And so in the context of recursion, what you can do is you can introduce memoization, right? You can eliminate redundant recursion with memoization. If you've not heard that term before, it's not memorization, it's memoization. Basically, it's just caching. Right? And I'll demonstrate it here in a moment. But caching meaning that to eliminate the redundant computations, you store them into a cache, a table. And once you've got this answer, you don't recompute it. You simply just look up in the table, have I already computed that before? If so, use it. If not, then okay, fine, I'm going to have to compute it. But once I've computed it, I put it into the table so I never have to recompute it again. Right? What we're going to do with dynamic programming is we're going to eliminate the remaining recursion by using a tableau. Right? And again, tableau is just another fancy word for a table. Right? We're going to do the bottom-up memoization instead. Instead of doing the recursion top-down, we're going to look at building a cache immediately using a table and a bunch of for loops instead of abusing the call stack to do our work for us. All right? So as a motivating example, and finally it's dying down here, motivating example, computing binomials. Right? So this goes back to the very beginning of this, where we were generating combinatorial objects. Right? So just a reminder, what are binomials? Binomial is basically a choice, n choose k. Right? Now there is a straightforward solution to this. Remember that you can you just apply a bunch of factorials, and you can get the value of this. And remember that n choose k, that's the number of possible ways from a set of size n that you can choose a subset of size k. So if you've got 10 people and you want to select 5 of them for a committee, 10 choose 5, that works out to 252, and you can just apply this this formula basically to get that value. Or alternatively, what you can use is Pascal's identity. And you might have seen this before when in the context of Pascal's triangle. You'll immediately recognize it here momentarily when we actually take a look at it later on. So here's Pascal's identity. N choose k is equivalent to saying n minus 1 choose k minus 1, and then sum that with n minus 1 choose k. Right? And there are a couple of base cases here, right? Because this is recursion, right? N choose k, I don't know how to do that, so I'll divide that up into 2 subproblems that are slightly smaller. N minus 1 and k minus 1, that's slightly smaller. N minus 1 choose k, that is also slightly smaller. And all I have to do is solve those 2 subproblems and add them together. Remember, we are on Piazza and YouTube. If you have any questions, please post there. But otherwise, our base case is going to be, well, if you have n elements and you want to choose one of them, there's really only one way of doing that, right? If I've got, choose n is the base case. If I've got 10 people and I want to choose them all for a project or something, well, I really have no choice. I just have to take them all, and so that's 1. Also, you can say that if you've got n elements and you want to choose nobody, right? Then that's another base case. So when n is equal to k, or when k is equal to 0, those are your base cases when you have no choice. There's only one, right? So let's go ahead and do some coding exercises here. Let's go ahead and just do the naive Pascal's identity here. So I'll go ahead and define a binomial method that takes n and k. All right. And let's go ahead and take care of our base cases first. Our base case is going to be when n is equal to k, right? Or when k is equal to 0. So if n is equal to k, or k is equal to 0, we'll simply return 0. Okay? Otherwise, we'll go ahead and recursively call this function binomial on n minus 1, k minus 1, and add that to n minus a call to the function with n minus 1 k. Right? And I'm adding those two together. Okay? So let's go ahead and test this out. I'll go ahead and define n to be 10, and k to be 5. Right? Just like I said before, 10, choose 5. If you got 10 people and you need to choose 5 of them for a committee, that's the number of ways of doing it. So let's go ahead and call a result here, binomial. Right? And why are they called binomials? Because they're binomial coefficients. If you take a binomial x plus y raised to the k, right, and you expand that out, the binomials correspond to those coefficients in that polynomial. And it's a binomial polynomial because you've got x and y. More combinatorics if that goes beyond the scope of this course, but hopefully you've seen it in 235 or some other discrete math course. So nk, and let's go ahead and print it out. So print the result, right? And I won't get fancy with my printing here, but let's go ahead and see if it works. Right. Oops. Oh, sorry. Duh. It's not 0. It is 1. Right. There we go. Of course, 0 plus 0 plus 0, I'll never get anything other than 0. Should be 252. Great. Let's go ahead and check ourselves. 10, choose 5 over here on Wolfram Alpha. Agrees with us when it pops up. 252, just as I said before. Okay. All right, let's keep going. What about if I had 100 people and I wanted to choose 50 of them for a much larger project? All right. Let's go ahead and find out how big that is. Remember that Python does natively support arbitrary precision numbers, Python 3, as of 3.6 or 3.7, I don't know. But it will, that's going to be a very large number, but it will still be manageable by Python. All right, while we're waiting for that, let's go ahead and go over here to Wolfram Alpha and see how big it is. All right. There we go. So I don't know how big that is. Here, octillion, 100 octillion or so. Okay, there are 100 octillion ways of doing that. We could sit here on the stream and sit and wait for this to execute. But let's go ahead and just understand why this is being so slow and maybe predict how bad it's actually going to be. Number of calls. What I'm going to do is I'm going to modify this to count how many times the binomial function method is called, right? And because it is a global variable, I'll need to designate it as such. And then down here, we'll go ahead and print the number of calls. Okay, so I'm going to go ahead and stop this, right? And let's rerun it, but let's rerun it for 10 and 5 and see just why it's so slow. And you can even see that it's a little bit noticeably slow. That's with even these small numbers here. And that's because to compute a value of 252 requires 503 function calls using this naive recursion. Right? So let's map that back over here. Well, we'll go ahead and let it try. Sure. All right. There we go. How big is that? Well, there's the result, 100 octillion, right? And remember that it's going to take like twice as many calls. But let's go ahead and just be generous and say that it only takes that many calls, right? And suppose that I can do 1 billion operations per second. There are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day, and 365.25 days in a year. How many years is this going to take to compute? Right. So 3 times 10 to the 12th. The number of it's 11 times, according to Wolfram Alpha, that's 11 times larger than the number of stars in our galaxy. It's 30 times larger than the number of people who have ever lived, et cetera, et cetera. So it's some huge number. That's the number of years that it's going to take to execute this program, right? And that's on the order of about 3 trillion years. So I don't have that much time in my stream here, live stream, so I'm going to go ahead and kill it, right? What was the problem? It was this naive recursion. When you call binomial of, say, 100 choose 50, that means that, say, binomial of 10 choose 5, that's being called billions and billions and billions of times, right? Why are you making the same function call over and over and over again when you could simply call it once? Fine, I have to pay for that computation, but then take that and put that into a table so that you can call it again, right? So I'm going to modify this to also take a table of results or values. I'll call it values. I'll still keep track of the number of calls, but before I actually compute, the values here, I'm going to check if nk is in my values, then I'll return values of nk. You can use a tuple as an index because what we're going to do is this is going to be a dictionary. So down here, values, it's a dictionary, right? And anything that is hashable in Python, you can use as an index value in a dictionary. Otherwise, else if, that means that I've not computed it yet. In which case I need to actually compute it, but instead of just returning a 1 immediately, I'm going to make sure that it's in my table. nk is equal to 1, and then I'll return 1. Right? Likewise, if it's not my base case, I will pay for the recursion. I'm going to have to call binomial on n-1, k-1, and n-1 and k, but I'm going to store that into a result. And instead of immediately returning, I'm going to set my table value of n and k to that result, and then finally return the result. All right, let's just go ahead and make sure I didn't break anything here. There we go. And of course I do need to pass it in, values. There we go. All right, let's go ahead and see if that made an improvement there. For 10 choose 5. 252 is still the same value as before, so I didn't break anything as far as correctness goes. But now I only have 52 function calls instead of the 500 or so before. So 1/10 as many function calls. And does that improve with 150? It certainly does. Only 5,000 function calls there, right? And you can see here, let me go back, 100 choose 50. That value is indeed matched. It was 100891, right, and ending in 256. I'm pretty convinced that it's correct, right? And that's what Wolfram Alpha must be doing. They must be using some sort of, well, they probably are using a lookup table or something. But when they're not using a lookup table, a pre-computed values lookup table, then they're probably doing something like this to compute the next value. Or they're just using the original formula right here, right? Okay. That's not yet dynamic programming, right? What I want to do now, let's go ahead and pre-print the values once we're done here, okay? Hopefully it nicely prints it, but there we go. All right. So what do you notice about this? This is the full table of the full dictionary, excuse me, of values here. It runs for n running from basically 1 up to 100, because that's our value over here. And it's running k from 1 up to 50. Actually zeros here as well because of the base cases here. So 0 up to 50, 100 and 0 up to 50. And it's printing all these values. Why did we need to use recursion at all to do this? Right? What if instead I had iterated a variable I and j, and then I came up with some sort of relationship that, what does that depend on, right? Well, it depends on previous values. If I replace I and j here, it depends on I minus 1 and j minus 1, I minus 1 and j, right? Let's look at that from the perspective of a table, basically, right? Now, this has been printed flatwise because that's how pretty printing works in Python. But what I could do is I could take each one of those coordinates and set them as a row and a column, and then look at it as a table instead. So let's go ahead and do that over here. All right. So what I will do is create a table here where n, where n is going to be over here. Actually, I'll go with I and j. And I'll create this table running from 0, for I, running from 0, 1, 2, 3, ... all the way down to n minus 1, n, right? That's going to be my n value here. And then my k values are going to be over here. K is going to run from 0, 1, 2, 3, ... k minus 1, and k. Right? Now, if I were to write all of those values in the table, what would it look like? Right? This one would be 0, choose 0, which is one of our base cases. When k is 0, it's going to be 1. Right? So I'm going to go ahead and replace that with 1. Likewise, anytime that k, that's this coordinate right here, is 0, then that's my base case. It's going to be 1, 1, 1, ... 1, 1. Right. What's my other base case? My other base case is when n is equal to k, right? Because when you go n choose n, that's equal to 1. All right? So, where is it equal? It's equal on the diagonal, right? 1 and 1, 2 and 2, 3 and 3. That's going to be 1, 1, all the way across the diagonal until I get to k, which is, remember, k is going to be less than n, because if k were greater than n, then you'd be outside this table. That means that you have, say, 5 people and you're trying to choose 10 of them. That's ill-defined. It doesn't work. Right? So all the way over here to k. Or, sorry, 1. Right? These are all invalid, right? Because, again, if k is greater than n, so, for example, k is 10, right? You can't choose have one person and then choose 10 of them, right? That's not going to be valid. These are all valid, though, right? And what values do they correspond to? Well, way down here at the bottom right, that's the one that I'm interested in. That's going to be n choose k. Now remember Pascal's identity here, Pascal's formula. N choose k is equal to n minus 1, k minus 1, plus n minus 1 choose k. Right? So to get this value, I just simply have to look up these two values in the table. Where are they? N minus 1, k minus 1 is going to be up and to the left. Right? And n minus 1 choose k is going to be in the same column, but one row up. Right? So in other words, this one is equal to this one and this one added together. Right? And hopefully you'll start to recognize this as Pascal's triangle. Right? Because now let's go ahead and compute this one. What about 2 choose 1? What is that equal to? it's equal to up the one immediately above it, and the one immediately above it, and to the left, and you add those two together. So this will be 2. Right? What about this value right here? The one immediately above it, and the one immediately above it, and to the left, I add those together. 3. Likewise, the same thing here. 2 and 1, add those together. 3. Let's do one more row. 1, and all the way over here is 1. Right? And then that's 4. Right? So what is that going to look like? This one is equal to the one immediately above it plus the one to the left. Immediately above it to the left. 4. Likewise, this will be 4. What about this one right here? That's the one immediately above it, and the one immediately above it to the left. 6. Right? And hopefully you can start to recognize this. If it weren't written in a tableau form, if it instead it was written in a triangle form, right? Then you'd recognize Pascal's triangle. Right? So all we need to do is fill out a table corresponding to Pascal's triangle in a straightforward manner, and we don't have to do any recursion at all. If for each one of these entries, for the I choose jth entry, we need to first compute I minus 1, choose j minus 1, and like in general here, if this is I and this is j somewhere, right? This is the one that where we want to compute. Compute the one immediately above it, and then the one immediately above it and to the left. Right, so, I is what I'm using now. I minus 1, choose j. Right? So I just need to compute these two. That gives you a hint as to how you fill out this table. First of all, you can fill out the base cases, or you can incorporate those into a basic loop. But to compute this one, you need the ones immediately above it. So if you just simply computed this, top to bottom, left to right, first, then you would have these values pre-computed for when you eventually get down here. Right? So top to bottom, left to right, that's just a basic for loop. For I running from 0 up to n, for j running from 0 up to k as an inner for loop, all you have to do is compute each one of these values. Right? And at the end, you have your final value right there. Okay? That doesn't require any recursion at all. That's just 2 basic for loops. Okay? So let's go ahead and go back over here to our code and see what that looks like. So I'll go ahead and retain binomial here. Let's go ahead and define a different function. What should we call this? Dynamic programming binomial. N and k. And the key here is I don't have to pass in a table of values. But I do need to create a table in order to do this. We won't... well, yeah, okay. Well, I guess we could do this. So let's go ahead and set up the table. All right. Other than using NumPy, I don't know how to set up an n plus 1. It's going to end up being an n plus 1 because we start at 0 and go all the way up to n by k plus 1 table. All right. It's Python. I don't want to set up a table. Setting up a table in this sense means that you are setting up a 2-dimensional array, which means that you're setting up a list of lists. Forget that. Let's just do a dictionary. A dictionary is a much more elegant solution here. Tableau, right, is equal to my dictionary here, right? And I'll use pairs instead. But I will develop the code to do this. So for I running from 0 up to n, right? And remember, we do have to go all the way up to and including n. So since range stops short, it's exclusive of the second argument there. Then I need to go up to n plus 1. Again, it'll stop at n. For j in range, 0 k plus 1. Right? All I need to do is look, well, first of all, I need to take care of some base cases here, which if, you know, these base cases over here, I'll just cut and paste this. Oh, well, cut and paste. There we go. I could have done this in a separate loop up above, but if I is equal to j or j is equal to 0, right, then I will set my value here of the tableau of I j to be 1. Right? Else, my tableau here is going to be of ij is equal to my already pre-computed table of I minus 1, j minus 1, and I minus 1, j. At the end of all this, I should have everything that I need, and all I need to do is look in that one location, return the tableau of n and k. No recursion here at all, just one function call. Right? Let's make sure that we actually get the same result here. In fact, I'm not going to pretty print it anymore, but let's go ahead and call result is equal to dynamic programming binomial on nk, and print the result. I don't need to print the number of calls here or to keep track of it because there's only one function call. I'm no longer abusing the stack space. Right? So let's try this out. Uh-oh. Darn. -1. Oh. So, if, let's see. Oh, I do, oh, sorry. I don't really need to start at 0 here. I'll start at 1, right? And then j, I don't need to start at 0 because I'm taking care of that in, well, no, I guess I can. I'm taking care of the that in my base case here. All right. So what was happening was that I was screwing up on the first iteration. Let me show you over here. This one right here, 0, 0. But that's only 1, and I don't need to. My base case will take care of that. I don't need to compute n0, so I won't run over that value. All right. Let's go ahead and try it again. Ah, darn it. Key value is bad. Let's see. Key value 0, 1. I'm still getting a 0 here. I saved it, right? Yeah, I did. Let's see. 1, 0. So j would be 0, but it would end up being this. I'm still getting n as being 0 here. So that's probably okay. All right, I'm cheaping out here. We'll go ahead and go back to 0, and take care of one more base case here. If n is 0 or all this stuff, the reason that we need to take care of so n being 0, 0 choose anything. That's the problem here is that we're going over the entire table. So let me go ahead and go back over here. Remember that these were invalid, right? So my for loop here could have been a little bit better designed. We are running from 0 up to n and 0 up to k, so we are ending up doing all of these things. We can go ahead and take care of that as invalid, or when you know. So we do need to take care of that. I think let's go ahead and try what we've got here so far. Otherwise, we can just ignore it. Yeah. All right, fine. So I'll make this into an else if. And the first if is going to be k is greater than n, or sorry, in this case, it's going to be j is greater than n, than I. Then we'll go ahead and make a tableau of -1 as a flag value to indicate that it's invalid. There we go. All right. We could have a better solution here would be to simply change the for loops that we're using. So let's actually go ahead and figure that out. Now that we've got a working solution, of course, commit that to our repo or whatever, and let's go ahead and go back and fix it so that we're not even considering any of these invalid values here. So if I run from running from 0 up to n like we did, right? Then what is my j going to run? Well, it'll run from 0 up to I. 1 up to a 0, 1, 0, 1. But only when it gets up to the n value here, I don't need to go any further, right? So I'm just going to skip all of these entirely by rewriting my inner for loop, so that I don't go all the way through each one of these rows that's invalid. Okay. So back to the drawing board here. I'll still start my range for j at 0, but I will only go up to and include I. That's why I'm going to do I plus 1. Right? And now this shouldn't be necessary at all, but I'll go ahead and leave it in there just in case. Right? There we go. So now I can go ahead and probably take this out just to test it and make sure that it works. Yep, there we go. So we're getting the same values. I'm convinced that it works, but we're doing it in a bottom-up manner. So again, to review the steps that we took, we started out with a naive recursion. That naive recursion turned out to be it would take billions and billions of years, trillions of years, to actually compute this small value here. Then we introduced memoization, where you cached all your results. You didn't recompute them and do all that redundant recursion. You put them into a table and looked up that table. So we did the recursion, but before we did went further in our recursion, we looked at that table and said, did we already compute this value? If yes, then we go ahead and used it. And if not, then we went ahead and paid for the recursion. In this last step here, we cut out the middleman entirely. The middleman being recursion. And what we did is we built the table up directly by identifying what the table would look like, by identifying this recursion, and then eliminated the recursion entirely using basic for loops. Okay? So let's outline exactly that approach here. Okay? And then we're going to look at another problem that you're already familiar with. So what are the basic steps to dynamic programming? So we identify a value that represents the desired solution or the optimal solution to a problem. All right. We identify a recurrence identity in terms of values of smaller problems. This is the divide part. And then ultimately we conquer it with the table, right? Now, if you need to, you of course might need to prove your recurrence is correct. With our previous example here, Pascal did that several hundred years ago. But basically, what you need to do is you need to show that there's this thing called this optimal substructure property, meaning that solutions to smaller versions of the problem, when you can be combined to provide a solution to the larger problem. Okay, so there's not really any hard and fast and rigorous definition of what that means. It's just a basic general process, and it's basically just induction, right? You identify trivial base cases, right? And you identify the desired final result. Right? And then what you do is you design a table or tableau, right? That holds values to each sub-solution. Right? And possibly, you may need to keep track of additional data in order to build the actual solution. Right? Then you design loops to fill in the cells of the tableau, so that subproblems are computed first. So that subproblems that are needed are computed first. Just like we wrote out the table for the binomial problem, and then we identified, well, I'm going to need the one immediately above it and the one immediately above it and to the left, your left. And so we came up with an idea. Well, what if we just went row by row, column, top to bottom, left to right? And if we did that, then everything would be available in the next row when we computed the next row. The last row, last column, that was our desired solution. Okay. You identify how those cells relate to each other, and so the proper order in which to fill them in. And then, of course, you implement your algorithm, right? You fill out the cells in the table in the order that you need them. Right? And that could involve doing a separate loop for all the base cases, but whatever. Right? So let's go ahead and look at an actual problem, and you will be programming this potentially. And the problem you've already seen before, but we're going to call it dynamic because, of course, this is dynamic programming. So the dynamic 0-1 knapsack problem. So remember that you are given a set of, or a collection, I should say, of items with weights and values and a maximum capacity. And I'll label it as W here, big W. We want to take as many items as possible to maximize our values subject to the weight constraint. You can't take too many, you can't take everything because everything weighs something and you have a maximum weight. If all the elements weigh 5 pounds and I can only carry 50 pounds, then I can only take 10 items, right? Which 10 items do you take? In that situation, you would take the ones that are most valuable. But certain things might have certain weights and certain values that don't necessarily, you can't necessarily be greedy about it. And we saw that when we covered the 0-1 knapsack problem and looked at a brute force solution for it. So again, we want to steal as much stuff as possible. So let's go ahead and take a look at one particular input example here. And this is just simply the one from the book, from my lecture notes set, I should say. It's not really a full book yet. But here's an example. Oops. So we've got 5 items in this case. A1, A2, A3, A4, A5. This might be the exact same one as example that we used before, but each one is going to have a weight, and each one is going to have a value. The weight here is, say, 5, 2, 4, 2, and 3, and the value is 10, 5, 8, 7, and 7. All right. And I forget what my weight capacity is here. My weight capacity W, big W here, is going to be 7. I can only carry 7 pounds. Pull to shoulder or something like that. I don't know. So I could take, one possible solution would be to take A1 and A2, right? The total value there is 15. And the weight is going to be 7. Again, where am I getting those numbers? Take those first two. There's the values. There's the weights. And it is possible to do this because my weight capacity is at most 7. Here's another potential solution. What if I tried to take A1 and A3? Right? So A1 and A3. The weight here would, of course, be 5 plus 4. 9. The value would be good. It would be 18, right? So this potential solution here has a better value, but it's an infeasible solution because my weight capacity is violated, right? So this is not possible. Another possibility would be, well, I could take, I don't know, I could take A1 and A4. Right, this one and this one. And I would have a value of 17. And that's even better. But what's the weight? It's going to be 7. And so that's feasible, right? Nice. Is that the best that I can do, right? That's the question that the 0-1 knapsack is asking. What is the optimal solution here? And you might be able to see it immediately, but I'm not. I don't see it immediately, so we're going to have to figure this out. Right? So let's go ahead and go through our process. That process being, let's identify a recursion, right, of the optimal value with respect to this problem. Okay. Let's go ahead. Excuse me here. Okay. So I'm going to set up a recursion here. V sub I j. And big V here stands for value. So this is going to be the optimal, the value, excuse me, the value of the optimal solution to the 0-1 knapsack problem. And remember, the 0-1 refers to the fact that you can take something 0 or 1, excuse me, or not take something 0. You can't take half of something. You can't chop it in half, and you can't divide it or anything like that. You have to just take it. But with the following caveats involving items A1 through AI, right? So in other words, we're only looking at a possible subset, right? Now, even within this possible subset, you may have taken some or some subset. Oops, sorry. Of these elements, right? But we're only considering the first I of them, right? Eventually we'll consider them all, but remember, we're looking for sub-problems. So if I've got 10 elements here, well, what if I restrict my attention to the first 5, right? And you can imagine where the base case is going to be. What if I restricted my attention to the first one only, right? And you can also imagine where the full solution is going to be. What if I considered all of 10 of those items, right? I'm looking in the middle there where I've considered items 1 through I, right? And what is about the J? Involving items A1 through AI with an intermediate weight capacity of J, okay? And again, you can imagine where J is going to run. What if I had no weight capacity whatsoever? 0, right? Then I can't take anything, so the value is consequently going to be 0. But then I'll consider, well, what if I could carry 1 pound? What if I could carry 2 pounds? What if I could carry 3 pounds, ... What if I could carry W pounds, where W is my total weight capacity? Okay? So I just described how I and J are going to behave. Let's note that here now, right? That I will run from 1 up to N, and J will run from 0 up to W, right? Y, again, I'll annotate this. Consider items 1 through N, A1 through AN, and we're going to consider weight capacities 0 through W. Okay? Now, given that setup, let's start identifying the other things. What are our base cases? What is the relationship between these things? Right? So let's go ahead and consider base cases first. Right? So the base cases are going to be when what if I've not considered any items yet, right? So if I is 0, right? Let me amend what we said over here. We are going to go to 0 here, but that's just to include this base case here. If I is 0, then we will consider taking nothing. Our better natures won out, and we're not actually stealing anything. Then in other words, excuse me. Sorry. Just distractions all day today. So 0 and then J. There. Comma J. There we go. That's going to end up being 0. If you don't take anything, then what's its value? Its value is 0. Right? Remember that v sub ij is capturing the value of the optimal solution. If you don't take anything, then you're not getting any value. Right? If j is 0, then you can't carry anything. Right? Both of your shoulders went out and you can't carry anything yet. So v sub I, j, or sorry, 0 is going to end up also being 0. Because you can't carry anything, you can't steal anything, so your ultimate value is going to be 0. Okay? So we've got our base cases. Now what we need to do is we need to find what the recurrence. So I need to get a handle on the actual v sub I, j. What is that equal to? Right? So I'm going to break this down into a couple of cases. Right? Again, this is the value of the optimal solution, considering elements or items 1 through I, with a weight capacity of at most j. So let's go ahead and consider case 1 here. We do not steal or take a sub I, the ith element. Okay? Well, if we don't take a sub I, then what is the value of v sub ij? Well, it's simply the value of v sub I minus 1 j. Right? If we're not going to take the element, then nothing happens to our weight capacity. But if we're not going to take the element, then basically we're saying, forget about a sub I. What about everything that came before it? A1 through I minus 1. What is the optimal value of that sub-solution? And we have a way to express that. We don't have a way to compute that yet, but we have at least a way to express that. So case 2, we do take a sub I. What is v sub ij in this case? Well, a sub I has some value, right? V sub I. Let me annotate that here. This is the value of a sub I. Okay? Plus, and now again we use our recursion here, where we've taken the ith value. What about the I minus 1 previous elements? Right? We've taken the ith item. What about the I minus 1 previous items? Right? You got to be careful here. What about our weight capacity? If I could carry 10 pounds, and I do make the decision to take a sub I, and it weighed 5 pounds, that means that remaining, I can only carry 5 more pounds. So when I consider items I1 through I, or 1 through I minus 1, I have to change my weight capacity, because by taking this element, I have reduced my capacity by a certain amount. And that amount is going to be W sub I. That, let me annotate that. That is the weight of the A sub I. Right? But I have to be careful here. Right? This is only possible if my weight capacity was at least as big as the weight of the ith item, right? So this is only going to be possible to take this only if, and another way of writing that is if j minus wi is greater than or equal to 0, right? And that's the way I subscripted it over here. Where did I get that? Well, you just take w sub I onto the other side, and that becomes 0, and you still have greater than or equal to here. Okay. But I could also choose, it might be feasible, right? If, in other words, this is feasible. But I could also say that, well, maybe taking the ith value is not the best approach. Maybe I could do better by leaving that one on the shelf and taking something else. So if it's feasible, I consider this. But if it's infeasible or that's not a better solution, I would end up considering not taking it. Right? So let's write this all out as one big formula. V sub ij is going to be equal to a couple of cases here. If j minus w sub I is greater than or equal to 0, in other words, it's feasible, right? I need to take the maximum of two things. The first one, where I don't take it, v sub I minus 1 j, and v sub I minus 1 j minus w sub I plus the value of I, right? If it's infeasible, then I have no choice. If j minus w is less than 0, then I have no choice and I have to leave a sub I. I can't take the ith element. So this will be v sub I minus 1 j. Right? This is the same as this up here. I have no choice. It's infeasible. This is no choice. But if it is feasible, then I have a choice. Whichever one it gives me the better solution is the one that is the choice that I make. Okay. Okay. Let's draw this out as a table. And to save time on this, let's see what time is it. Yeah, to save time on this, I will simply bring in the table from the notes. Let's say 01 knapsack. There we go. Okay. There we go. Remember that we're running I for 0 up to n. These are items over here. The first row, of course, would correspond to our base case here, where you don't take anything. And so all of these are going to end up being 0. The first column over here, where all the columns are corresponding to weights, weight capacities. If you can't carry anything, then it's going to have a value of 0. Right? So along the first row and along the first diagonal, those are going to be our base cases. And then, of course, we consider each item, the first item, then the second item, then the third item, ... until we get down to the last item. For all of the weights, we consider weights 0, 1, 2, 3, 4, all the way up to the big weight capacity here. Okay. The one that we're most interested in is the one down at the bottom right. And that's just because that's how I presented it. It's not necessarily the same thing as the binomial coefficients. It just gets it ends up being almost the same solution as far as the for loops go, but with different criteria. We're still interested in the bottom right here. Most problems will have a solution that looks like that simply because that's the way you think. Right? You in English you read top to bottom, left to right, right? And so we'll naturally want to produce a table that looks like this. Okay. So remember v sub ij here, right? We derive this formula here that it's dependent on I minus 1j. Well, where is that thing? I minus 1j, the one immediately above it, just like the binomial coefficients. And what about the other thing that it depends on? The one immediately above it, but then not immediately to the left. It's to the left by some factor, j minus wi. Wi is just a variable. We don't know what the value is. So I've taken the liberty of labeling it over here. Right? So in other words, this value is going to depend on the one immediately above it and some value in the row immediately above it and to the left. Right? We don't know where that is. But it still tells us what kind of strategy to come up with to actually program this. All we need to do is start at the top left and go left to right, top to bottom, just like we did with the binomial coefficients. If we are sure to do an entire row before we go on to the next row, then all of those values are going to be available, including the one right above it and the one above it and to the left by some factor. right? So all we need to do is set up the same exact for loops here, but there are no invalid areas here. The first column and the first row, those are going to be invalid, but all we need to do is make sure that we go top to bottom, left to right. Okay. I hesitate to write the pseudocode because it's so simple, right? So for I running from 0 up to n, for j running from 0 up to w, right? All you need to do is compute the results. Like if j minus the weight of I, right? Remember this is the big W, right? Is greater than or equal to 0, then we have a decision to make. It's feasible, right? There I am doing Python. Ugh. So it's feasible. So we take the maximum, right? If the value of, and then here we're codifying that here, that this is feasible, and so we'll take this value and this value here. V sub I minus 1 j is greater than V sub I minus 1 j minus W sub I. And remember, we're not going to have any index problems here whatsoever because we've already verified that this is greater than or equal to 0. That means that not taking it, A sub I, is a better solution. And I'll just say right now that you could have multiple optimal solutions with different elements swapped in or out, right? So we will update V sub I j to be equal to V sub I minus 1 j. There we go. Else, it's not feasible. It is feasible. We're not there yet. That would be this else here, right? Else, V sub I j will end up being the other one, this one over here. Copy. Paste. There we go. I'm going to do the same thing with the other one, right? So otherwise it's not feasible. Right? And so we take this solution right here. Copy. I think I get too much, but all right. Paste. There we go. I just like that feature so much. All right. There we go. Done, 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 and done. Now, to do, initialize base cases. And when you do that, you don't need to start at zeros, right? Because for the first row, if you do that separately, and for the first column, if you do that separately, then you can restart, and I will annotate that here. You only have to start at 1, right? If you've done this to do over here, okay? All right. Unfortunately, that doesn't tell us how to actually build the solution, right? What I mean by that is that input that we looked at earlier, and for that I'm going to cut and paste that. Where is it? There we go. Copy. All right. There we go. There's my example from before. So fast forward here, and you can see the actual filled out tableau here. Right? Now, again, let's look at this tableau before we look at the details of it. 0 through 5, that corresponds to not taking something. A1 corresponds to I being 1 over here, A2, A3, A4, A5. And then each one of these weight constraints corresponds to a capacity of 0. You can't take anything. You can take 1 pound of stuff, 2 pounds of stuff, 3 pounds of stuff, until you finally get over here to 7 pounds of stuff, right? And this is the final tableau here. That only tells us what the value is, 19. Which ones of these did we take, right? I have no idea. You could look at this and derive, well, what subset of values here sums up to 19, right? But then you'd be resolving the problem, right? What I'm going to do is I'm going to show you the basic idea, and then when we come back tomorrow, we'll go ahead and actually develop the pseudocode for it. This is my ultimate solution right here. That's the one that I want, right? When we chose 19, we had made a decision. When that table was filled out, we looked at the one right above it, and then some value over here. Which one? I don't know, right? And we made a choice of taking it or not taking it, or we didn't have a choice and we didn't take it at all. By looking up one above, what can we deduce here? Right? Did we take the value that didn't include a sub I, or not? These two values are different here, 17 and 19. What that means is that you made a choice to take a sub I. Otherwise, these would have been the same number, right? If you had not taken a sub 5, then you would have just simply copied down the number from right above it, right? Remember what that looks like. Let me get rid of these, right? So what value? If this value is simply copied down, that means that you're not changing the weight capacity and you did not take the item. Otherwise, if the number is different, then that means that you did take this value over here and then you added in the value of the ith value or ith item. Right? So if this value is just simply copied down, that means that you didn't take it. If it's different, that means that you did take it. Now, of course, it could be the same and you did take it. It's just that that's just a difference of greater than or equal to over here. Right? That's just, forget about that though. It'll lead to the same solution. Right? So let me demonstrate how to go about doing building the solution. Right? So these are not equal. So you took a sub 5. So now I'm going to continue in this table. I took a sub 5, and now I'm going to consider all the values 1 through 5. But remember, I took a sub 5. That means that my weight has changed, my weight capacity. That weighs 3 pounds. I can now only carry 4 pounds. Right? So what I'm going to do is I'm going to traverse over here to 4. Right? And that's where I continue. This is not the same thing as 8. So therefore, I took A4 as well. By taking A4, I'm changing my capacity again here. There's only, now I have 4 pounds to play with, but now I'm down to only 2 pounds because A4 weighs 2 pounds. So I need to jump over to this column. Now I look at the one right above it. They are the same. That means I did not take A3. I did take A5, I did take A4, but I did not take A3. Okay? I can continue, right? So I didn't take A3. Now look at this column and compare it to the one right above it. I did take A2 because those two things are not equal. A2 has a capacity, or it has a weight of 2, and so now I'm down to 0, at which point I stop, right? I do jump over to this column here, see that 0 and 0 are the same, so I did not take A1, or I did not take A1, excuse me. And then I shouldn't have crossed out 0 because that's not even an item. Right? So I took these three items right here. A1, or sorry, A2, A4, and A5. That's my one of my optimal solutions, and it has a total value of 2 plus 2 plus 3. Well, I know that already. It's 19. Sorry, the value is 5 plus 4, 7 plus 7, and the value is 19. And the weight is 3 plus 2 plus 2, 7. I've maxed out my weight capacity there with this solution. Right? And that's much better, I think, than any of the ones that we came up with. But I don't remember what we did. I just randomly chose elements. What were they? 15, 17, 18, but that was infeasible. So, yep, we did much better there. Okay? So, when we come back next time, we will codify this in pseudocode. Then we'll look at the complexity of this. It is actually quite subtle to look at the complexity of this. Of course, you're filling out the table here. So you might say that, oh, it's like n squared or something like that, because this is an n by, well, m, it's an n by w table, so maybe it's n w, something like that. W sounds like a constant to me, so it looks linear. Nope, this is it's pseudo-linear, right? That's what we call it. W could actually be much, much larger than n. It could be exponential in the size of n. So you might end up making a table that is exponentially big and then filling it in. Basically, you're just hiding the work in the size of the table rather than in the for loops that we developed. And this problem is one of many that is NP complete. We will start talking about complexity after dynamic programming, but no, we did not come up with a polynomial time solution to an NP complete problem. That nobody knows how to do that. It's probably unlikely that that's true. We just basically cheated and hid the complexity of this algorithm in the size of the table. Okay. I see no questions, so I will see you in office hours. Otherwise, I'll see you tomorrow when we conclude, hopefully conclude dynamic programming. Have a good day.